All right, hello everyone, and welcome to my channel. This is an educational channel, and we look at old and new theories of everything, things that you can hang your hat on, things that are cosmologically significant, and that you can build your paradigm around, your new paradigm, moving into the 5D world, and making the transition to higher consciousness, great awakening. Today is our 417th video on the reciprocal system of theory from Dewey B. Larson. Mr. Larson was born in 1898. Around 1930, he was a mining engineer, fought in World War I, and became an engineer after that. Was kind of diddling around, working on a few different science projects, trying to make some small contributions in his field. Stumbled across some potentially earth-shattering ideas, answered the call, and did a lot of 25, 30 years worth of research to kind of work out his ideas. In 1959, he proposed his two fundamental postulates. He had all his ideas boiled down to two sentences that he said this is how the universe is constructed. And then he took those postulates and he developed a theoretical universe through a process of if this, then that. He determined the characteristics of his universe, of his theoretical universe, and then in the remaining years of his life up until his death in 1990, he was writing books more or less comparing his theoretical universe with the empirical and measured universe of the legacy scientists. And in many cases, he had very similar, if not identical, results. But Mr. Larson was doing that on a minuscule budget with no modern tools and no other resources, no other people helping him. And it took the scientists multi-trillion dollars and probably hundreds of thousands of them over the course of centuries to come up with their tables. So Larson's got a powerful theory there if he's able to come up with the same answers just off of his theory, off of his top of his head. So basically, his two postulates read as there are a few different versions of them, so it's hard to quote them directly, but the universe is composed of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. And then the second postulate, which is not as important, is that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. So the first postulate is what we want to focus on here. Basically, the universe is not made out of matter. It's not made out of energy. It's not made out of the 4 fundamental forces. It rather is made out of motion. In particular, Larson identifies a kind of motion that is more unfamiliar to us, that is less localized and more general, that is called a scalar motion. A scalar motion is a motion that has a magnitude, but it has no specific direction. Or really, its direction is either in or out. You can envision a scalar motion if you envision a balloon with dots on it, or spots on it. As you blow up the balloon, all of the spots will be moving away from each other. they're not moving in any particular direction, just away from each other. Every spot will be moving away from every other spot. And in fact, even the locations that are between the spots will be moving away from every other location on the surface of that balloon. They're all moving away from each other, but in no particular direction. That is a scalar motion. You can fill in the third dimension if you imagine something like raisin bread, where you put the bread in the oven, it begins to rise. All of the raisins will be moving away from each other, but again, not in any specific direction. The further away they are, the faster they'll be moving away from each other. That is a scalar motion. And that is the motion that, even though the legacy scientists know very little about scalar motion, they do admit to its existence. They've observed that all of the distant galaxies are moving away from each other. But they have not recognized its significance. For Larson, he builds his whole universe on that scalar motion moving outward. That is his background motion. And the rest of the universe is built off that motion. Now, the reason why Larson calls it the reciprocal system of theory, first of all, it's a system of theory, meaning that if you get the theory, you can plug in the reciprocal system to any subject. It doesn't matter what it is. You can plug it into, underwater basket weaving, the reciprocal underwater basket weaving. I'm a historian. I would like to apply it to history. Larson himself has applied it to economics. He's got 2 books on economics. One is called The Road to Full Employment, and the other one is called The Road to Permanent Prosperity. We are going to look at that second book, The Road to Permanent Prosperity, coming up here pretty soon. In a couple months, we're going to go over that book. It's very interesting. And but most of Larson's books are on scientific topics such as physics and chemistry and astronomy. But he also has a book on metaphysics, which includes sections on philosophy, religion, and psychology and biology. So he has, employed his system of theory. The reciprocal part of the reciprocal system of theory applies to the relation between space and time. Motion is the relationship between space and time. That sets up a generalized reciprocal relationship between space and time. Basically, motion is a fraction, with space or time as the numerator and time or space as the denominator. Space and time, however, come in 3 dimensions, so that complicates things. But all of our scientific quantities are forms of motion. So matter is a kind of motion, energy is a kind of motion, force is a kind of motion, acceleration is a kind of motion, pressure is a kind of motion, electric current is a kind of motion, electric charge is a kind of motion, electrical capacitance is a kind of motion, magnetic flux is a kind of motion, permeability is a kind of motion, viscosity and fluidity are kinds of motion. They all have their own specific space-time coordinates. So that is the part of the 3-dimensionality of space. 3 dimensions in a still frame. The temporal reference system and the spatial reference system, not respectively, but separately. They are 2 separate. And generally, the spatial coordinate system goes together with the scalar time system. So a scalar motion in space is coupled with a coordinate motion in time and vice versa. Scalar motion in time is coupled with a coordinate motion in space. We're familiar with the latter really only. In our sector of the universe, we observe relations based on 3 dimensions of space in a still frame and time moving in a scalar manner, or the flow of time. Time is always getting farther and farther and farther apart, like on the surface of an expanding balloon. But if we were in a different sector of the universe, we would observe 3 dimensions of time in a still frame, and we would see space as flowing or progressing. Space is always getting farther and farther and farther apart, like on the surface of an expanding balloon. And that sector of the universe is what Larson calls the cosmic sector. Now, the cosmic sector can be derived out of the discrete unit postulate. We said that the universe is made out of motion. Motion is a relationship between space and time, but the motion universe is constructed out of motion, existing in 3 dimensions, like coordinate space and coordinate time, in discrete units. So space and time both come in only discrete units. You have to have a full unit of space before you have space. You have to have a full unit of time before you have time. If you don't have a full unit, then you don't have those qualities, those quantities. And if you have 1 unit of space in 1 unit of time, space over time being speed, you have what Larson has called unit speed. 1 over 1 equals 1. Unit speed is also the speed of light. So the speed of light is the kind of the background motion of the universe. It's the midpoint. Einstein sees it as the maximum speed of the universe. Larson sees it as the midpoint, meaning that there's an entire universe that Einstein doesn't know anything about that is moving faster than the speed of light. Larson refers to that as the cosmic sector. And that is where you have the relationships that are based on coordinate time and clock space. 3 dimensions of time in a still frame, and space is always moving farther and farther and farther apart. Contrasting with the material sector of the universe, which is a sector that we are accustomed to, that we live in, and that is moving slower than the speed of light. Okay, now we are looking at chapter 2 of Larson's book called Basic Properties of Matter. Basic Properties of Matter is a book where Larson derives equations for it's on chemistry, derives equations for the basic properties of matter, and then compares them with the scientific tables. In this chapter, which is called Inter-Atomic Distances, Larson attempts to specify the interatomic distance for all of the different elements. The hydrogen and the helium and the beryllium and boron and lithium or not in that order, carbon, all the way up to uranium and beyond. And he comes up with various equations. The basic gist of it is, well, first we have to figure out about the time region and the space region, in particular the time region. If you don't have a full unit of space, then you don't have space. That's the discrete unit postulate. If you don't have space, then you only have time, because the universe is made out of space and time, motion. So if it's not space, then it has to be time, or both. And so you don't have space, that means you have only time. So when you have an interaction that occurs in less than 1 unit of space, and 1 unit of space is 4.56 times 10 to the minus 8 meters, so approximately 1/500,000th of an inch, then you only have that interaction in time, because it's less than 1 unit of space. So you don't have space, you only have time. Larson calls this the time region. And the time region is where we have interactions of atoms and particles, material atoms and particles. Cosmic atoms and cosmic particles, or what we call antimatter, they interact over in the cosmic sector. where the speed is faster than the speed of light, and the activity occurs in less than 1 unit of time, where time is 1.52 times 10 to the minus 16 seconds. So less than that instantaneous kind of time interval. Then if you have interactions less than that, then you don't have time, you only have space. So the interaction occurs in what he calls the space region. When you cross those boundaries, cross the unit speed boundary, you have to switch the roles of space and time. Where you have to cross the unit space boundary, then you have to, or the unit time boundary, then you have to reverse the order of the primary forces. The progression, which is the outward movement of the balloon surface, that is the outward movement. When you blow up the balloon, all of the dots are moving away from each other. Larson calls that the progression. And when that occurs at the speed of light, that is the progression of the natural reference system. When you suck in the balloon and the balloon contracts and all of the dots are moving toward each other, Larson refers to that as gravitation. The interatomic distance is the equilibrium between those two forces. Now, when you have those forces in the time region, they act opposite. So normally the progression is moving outward and gravitation is moving inward. But when you are within 1 unit of time or space, then the progression is moving inward and gravitation is moving outward. And this enables an equilibrium between the two forces. And so the progression is constant. It's always moving outward at the speed of light in all directions. Gravitation is variable depending on the distance apart that the two apparently interacting particles are. And so you have to find the place where gravitation is equal to the progression, and that is the equilibrium point, or what Larson calls the interatomic distance. So we're going to go into this chapter. This is our third installment of this, so if you want to catch it at the beginning, you want to go back probably really about 10 days to get chapter 1 also. And chapter 1 is on solid cohesion, which is a similar topic that leads into this. Okay. The regular electropositive pattern. Electropositives are the kind of the left side of the periodic table. The regular electropositive pattern is also applicable in division 2, which is the left side of the periodic table with valence greater than 4. And a number of the division 2 elements of group 3A, which is the row with, I believe it's the row that goes from sodium to argon, but it might be the row after that, from potassium to krypton. We'll see. And a number of the division 2 elements of group 3A, yeah, I would think, okay, crystallize on this basis. Crystallization is what happens when you move into the time region. And that is the part of the, interatomic equilibrium. Number of the elements of group 3A crystallize on this basis with interatomic distances determined in the same manner as in division 1. As noted in volume 1, which is called Nothing But Motion, however, the division 2 elements generally favor the magnetic type of orientation in chemical compounds because the normal positive orientation becomes less probable as the displacement increases. The same probability considerations operate against the positive orientation in the elements of this division, but instead of employing the magnetic orientation as the alternate, these elements utilize a type of orientation that is available only where all rotations of each participant in a combination are identical with those of the other. This arrangement reverses the effective directions of the rotations of alternate atoms. The resulting relative rotation is a combination of x and 8 minus x, or in some cases 4 minus x, as in the neutral orientation. And the effective specific rotations are 10 for vibration 1 and 5 for vibration 2. A combination value of 5 or 10 is also common. Larson's kind of in the weeds here. I don't feel like this is all that crucial, but he does have a table here where he compares his calculation for the specific for the interatomic distance with the tables, and this is all measured in angstroms. And he starts here with 2b, which is, I guess, 2b is the row from sodium to argon, and then I guess 3a would be the row from potassium to krypton. And so sodium specific rotation 3 dash 2.5, and then it also has an orientation where it can be 3-3. His calculated value is 3.70 angstroms. The observed value is 3.71. For magnesium, specific rotation 3, 2.5. Let's see here. I'm not sure what this second number here is in the table, but his calculation is 3.17. The observed value is 3.21. Aluminum, number 13 on the periodic table. Calculated 2.83, observed 2.86. Then moving to elements 3A in the 3A row, potassium, number 19, calculated 4.49, observed 4.50. Calcium, number 20, calculated 4.00, observed 3.98. Number 21, scandium, calculated 3.18, observed 3.20. Titanium, number 22, calculated 2.95, observed 2.92. Then moving to the 3B row, starting with rubidium, number 37, calculated at 4.85, observed at 4.87. Strontium, 38, calculated at 4.32, observed at 4.28. And on and on and on. And he actually just calculates a few in each row, or shows the calculation here. And in all cases, he is relatively close. There aren't any cases where he's more than just over 1% of the value away from the observed value. And now back to the text, he's saying that he's talking about a reverse orientation, which I think is when the specific rotation is aligned in a different way, and then has different numbers that go into the interatomic distance. Each one of these elements, there are different options for it to take. Some only have one option because only the one option is much more probable than any of the others. But then in some cases, the probabilities are fairly similar. And so there might be two forms, or maybe even more than two forms of orientation of one particular atom. And so they might have more than one interatomic distance. And he's saying this reverse type of structure makes its appearance in the body-centered cubic crystal forms of chromium and iron, which coexist with the regular positive hexagonal or face-centered cubic structures. Vanadium and niobium, the first division 2 elements of their respective groups, combine the positive and reverse orientations. Beyond niobium, and the positive orientation does not appear in the common division 2 forms of the elements. The structures to which the present discussion is limited, and all elements take the reverse orientation except europium and ytterbium, which combine it with a unit-specific rotation, that is, no electric rotational displacement at all, as in the inert gases. Okay, Larson is more or less writing this for an audience of chemists. So he may have gotten you lost, as he got me lost, as we move through this. And he keeps kind of diverting away from, the actual theory, and he gets into some of the finer points. And I wish that Larson would do that with footnotes instead of putting it into the text. I think it would make it easier to read, but it's kind of impossible to second guess Larson because he was doing this all by himself and he had no resources to do it. And I know it's very, very difficult to articulate a new paradigm. You have to use a whole new vocabulary to articulate points that have never been made before. So, I'm not going to criticize him for, not using footnotes. But that's what I would have done. But I might be wrong. This might be a better approach. I don't know. But it's causing me to get a little bit lost here. And I suspect you might be too. Figuring out all of the different orientations. But the bottom line is that Larson was able to predict these interatomic distances, at least of those particular particles, of those particular atoms, with that equation that he used that was introduced in yesterday's video. On the basis of the considerations discussed in Chapter 1, the average effective specific rotation for such rotational combinations has been taken as the geometric mean of the two components, where the orientations are the same and the only difference is in the magnitude, as in the 5-10 combination and in the combinations of magnetic rotations that we will encounter later. The equilibrium is reached in the normal manner. If two different electric rotations are involved, the two atom pairs cannot attain spatial equilibrium individually, but they establish a group equilibrium similar to that which is achieved where n atoms of valence 1 each combine with one atom of valence n. The division 2 distances are shown in Table 3. So here he's covering the division 2 elements of row 3A. Apparently that begins with vanadium, number 23. Calculated 2.62, observed 2.62. Chromium, calculated 2.68, observed 2.72. In its alternate form, the other orientation, where it's chromium is element 24, it could either be attracted to the zero, to the argon, number 18. So it has a specific rotation of 7, 6 plus 1, or to all the way over to the other side of the other noble gas, being krypton, number 36. That would give us a valence of 12, but apparently the specific rotation is always going to be 10. So with a specific rotation of 10, he calculates 2.46, and the value is 2.49. So chromium has 2 alternate versions. Manganese, number 25, for some reason only has 1 version, and that is calculated at 2.59, observed at 2.58. Iron, calculated at number 26, calculated at 2.56, observed at 2.57. For the first orientation, which is specific rotation 8.5. Second specific rotation is 10. And this specific rotation is in the electrical, the third number. Every atom has 3 numbers. 2 of them are magnetic rotations, and 1 of them is an electric rotation. Matter is based on 2 photons, which are vibrating units, or simple harmonic motions. They're wave-like motions, and they are at the core of the atom, but they are moving outward at the speed of light in all directions. And in order to slow them down and stop them and get them to gravitate, you have to rotate those photons in 3 dimensions to stop them. And so that is what the periodic table is based on. You have to rotate it in 2 dimensions, magnetically primary, and 2 secondary 2-dimensional rotations. That makes 3 total, and 3 total dimensions. Okay, we'll start again tomorrow.